Let's take a look at PNP transistors. A lot of students don't like these because the voltages all seem to be negative or turned around. There's a trick that I want to show you for dealing with these PNP transistors. First, let's take a look at one of these transistors and I'll show you what to do. The key to understanding circuits that have these PNP transistors in them is to make sure the circuits are drawn with the arrow pointed downwards and with the voltages arranged high to low as you look from top to bottom. Now the PNP transistor has an emitter that's doped P-type, a base that's doped N-type, and a collector that's doped P-type. What you want is the emitter to be at a higher voltage compared to the base, and you want the base to be at a higher voltage when you compare it to the voltage at the collector. In other words, we want the high voltages at the top and the lower voltages at the bottom. When I say voltages, I'm talking here about positive voltages. We're not going to be worried about negative voltages so much in this trick. You might notice here between the emitter and the base junction is a forward bias diode. To turn on the transistor, we need to make sure that the emitter base voltage exceeds the turn-on voltage for a forward bias diode. That's about 0.7 volts if the transistor is made here from silicon. Just to make it clear, let's label the emitter voltage as V sub E, the base voltage as V sub B, and the collector voltage as V sub C. And something that you might notice when you compare this transistor to the NPN transistor is that we have the emitter up at the top. I know it's the emitter because I see where the arrow is. The arrow points either from the emitter to the base, like here in the PNP transistor, or it points from the base to the emitter in the NPN transistor. In either case, that's the side of the transistor that contains the emitter. With a PNP transistor, we want the emitter up at the top. We're now going to work a few examples to bias the PNP transistor. We want it to be operating normally in the forward active mode. One thing I should point out, though, is that the PNP transistor is generally not as good as the NPN transistor, and the reason for that boils down to the fact that the emitter has the highest doping in a transistor. If it's an NPN transistor, then the emitter is doped N-type. If it's a PNP transistor, the emitter is doped P-type, but in either case, it's the emitter that has the heavy doping. Since in a PNP transistor, it's the holes that are the majority carriers, and holes have a lower mobility than electrons, which are the majority carriers in NPN transistors, the PNP transistor ends up not working as well. So it boils down here to the mobility of electrons being better than the mobility of holes. What we can conclude then is that PNP transistors are not exactly opposites to NPN transistors. There's a difference in quality. In any case, let's get some practice working with these PNP transistors because you still need them sometimes. Let's find the mode of operation. Now, PNP transistors, they have the same four modes as NPN transistors: cutoff, forward active, saturation, and reverse active. So that's what we're looking for when we work this example. When I see this example, I first take note that it seems like it might be forward active because we've got high voltages at the top, low voltages at the bottom, the arrow's pointed in the correct direction, and my resistors seem to be reasonably chosen. I have a factor of 10 here on the left side compared to the right side. So I predict forward active just by inspection. Let's see how the voltages work out. We have 9 volts that's going to divide evenly across these two 10 kilo ohm resistors. That's going to put my base voltage right around 4.5 volts. We now know that the emitter base voltage drop has to be somewhere near 0.7 volts. So I can use this information to find the emitter voltage by assuming that the transistor is turned on. If I reach a contradiction, I'll know that it's not turned on. All we need to do then is to add 0.7 to my base voltage, and here we wind up with 5.2 volts. That's less than 9. So far, so good. If it were more than 9, it would mean that current would be flowing the wrong way through that resistor. Here we're okay. Let's label that current as the emitter current and find it. I can just apply Ohm's law to this 1 kilo ohm resistor. We have 9 minus 5.2 volts across it, and the resistor is 1 kiloohm. That gives me 3.8 milliamps. If it's a well-designed amplifier, then the collector current should roughly equal the emitter current. This means that my voltage at the collector can be found by Ohm's law. It's just my collector current times my collector resistor. We have 3.8 milliamps for the collector current and 1 kiloohm for the collector resistor, 3.8 volts. So take note of our voltages. High, medium, and low. Everything looks good. The only other remaining question is whether the base current is negligible. The base current here is going to be flowing out of the transistor, unlike the situation in an NPN transistor where it would be flowing inwards. If the base current is negligible, it means my calculation of the base voltage here, 4.5 volts, is accurate. On the other hand, if there is substantial base current flowing out of that transistor, then it'll cause my base voltage to be higher than what I calculated, and everything could be screwed up. The base current is related to the collector current of a transistor by a factor of beta, and we usually say that beta is something like 100. So in this case, it works out to be 0.038 milliamps. When we want to know whether it's negligible or not, we need to compare it to the current running down through this resistor. I'll label that I1. I1 can be found by applying Ohm's law to this 10 kilo ohm resistor. So we have 4.5 volts divided by 10 kilo ohms, 0.45 milliamps. Well, it's more than a factor of 10 difference, so I'm going to say, yeah, the base current is basically negligible here. Since we have our voltages arranged nicely from high to low, the arrow's pointed in the right direction, and the base current is reasonably negligible, I can conclude that this transistor is in the forward active mode. Let's work another example. Now, what I first notice is that we have a really big resistor down here, and that's probably going to cause some problems. Let's find what our base voltage is. It's going to be a voltage divider set up by the 30 kilo ohm resistor and the 1 kilo ohm resistor. So up here in the numerator, we should have 30 kilo ohms, and then down here in the denominator, we have 1 plus 30 kilo ohms. And we wind up with 9.68 volts at our base. Let me write it right here on our base. Now the question is, can our transistor turn on? Well, we know to turn on, we have to have at least 0.7 volts from emitter to base. If I take my base voltage and I add 0.7 volts to it in order to find my emitter voltage, then what I'm going to get is a number that's greater than 10 volts. That voltage can't be correct because it would imply that current is going to be going that way through the transistor. VE can't be higher than 10 volts. I've reached a contradiction. There isn't actually 0.7 volts across that junction. The reality is that my emitter voltage remains at 10 volts. I have zero current flowing down through that transistor, and I have insufficient voltage to turn on this transistor. We only have 0.32 volts from the base to the emitter. Taken together, that just means that our transistor is in cutoff. It's cutoff because there's no current flowing, and there's no current flowing because I have insufficient voltage across the emitter-base junction to turn it on. In example 3, when we first look at it, everything seems to be okay. We have a factor of 10 difference between the left side of the circuit and the right side of the circuit, and current seems to be going down. The arrow is pointed from high to low, but when you look at the power supply voltage, you can see that we've got a big problem. We have minus 10 volts up here at the top, and we have ground or 0 volts at the bottom. What we have here is a circuit diagram that's very poorly drawn. It's got the negative voltages at the top and the ground down at the bottom. I don't like that at all. So the first thing I'm going to do with this problem is to flip the circuit so we have the high voltages up at the top where they need to be. Let's redraw it with the high voltages up at the top. So I'm going to start with 0 volts or ground, and I'm just going to redraw the circuit looking up. So we have two 10 kilo ohm resistors over here on the left. Let's label our power supply as -10, and then we have our transistor. Now this is very strange because the arrow is no longer pointed downwards when I write the circuit from high to low, so it's probably not going to be in the forward active mode. But because everything else looks to be okay, I think this circuit is probably in the reverse active mode. It's a PNP transistor, so we know that at least it's theoretically possible for the collector to behave like an emitter and for an emitter to behave like a collector. Let's assume that it's in the reverse active mode and that current is properly flowing in this direction through the transistor and see what the voltages are. I know this is the collector, but I'm going to label it as VE, where E is emitter. And I'll put the E in quotation marks because it's not the real emitter. Let's do the same thing down here for the emitter. I'm going to label it as the quote-unquote collector. The base is the base, so I'll just leave that be alone. Let's now proceed. We have a voltage divider set up by these two 10 kilo ohm resistors. That should put my base voltage midway between my two rails, so we should be at -5 volts. My emitter voltage needs to be at least 0.7 volts higher than my base voltage in order for the transistor to turn on. That would put my emitter at -4.3 volts. Let's label the current flowing down the right side of the circuit as I. I is then just 4.3 milliamps. And because the 4.3 milliamps is flowing down here as well, we have enough information to find our collector voltage, where it's not really the collector, but it's going to be above our lower power supply voltage by I times R. And it works out to -5.7 volts. Let's label our voltages on the circuit diagram. We have -4.3 volts here at the emitter. We have -5 volts at the base. And we have -5.7 volts over here at the collector. Current seems to be moving in the correct direction through the transistor, and I would say ordinarily this is the forward active mode, but because I started off by flipping the transistor upside down, I'm forced to conclude that the transistor is actually in the reverse active mode, where the emitter behaves like the collector and the collector behaves like the emitter. I should point out that these transistors in the reverse active mode tend not to do very well. And I went ahead and simulated this circuit with LT-Spice to see how the voltages would actually come out. The simulator says that the base voltage is -2.6 volts. The quote-unquote emitter voltage is -1.9 volts. And the quote-unquote collector voltage is -8.5 volts. Let's draw those on our circuit. You can see that the voltages are still properly arranged from higher voltages to lower voltages as we look down our circuit diagram over here in the reverse active mode. But you can see that the voltages don't match very well what I calculated, and that's really a symptom of a problem. And the problem here is that you shouldn't operate a transistor in the reverse active mode. But at least our method here was powerful enough that we could predict the reverse active mode. Let's move on to example 4. At first glance, everything seems to be okay. We have 10 volts at the top. We have ground down here at the bottom, so we're okay in terms of the voltage flow. The arrow seems to be pointed downwards, which matches the direction of current flow. So far, so good. I expect the base voltage here to be about 5 volts. The emitter voltage needs to be 0.7 volts higher than the base voltage, which is 5.7 volts. That's lower than 10, so that's good news for this current flowing in the right direction. Let's label it the emitter current. and find it. It's going to be the voltage drop across this resistor, which is 10 minus 5.7 divided by the resistance, or 4.3 milliamps. The same current should be flowing down here through our collector, approximately. And we then have enough information to find our collector voltage, which works out to 8.6 volts by applying Ohm's law. I hope you've noticed that we have a problem. We have 10 volts at the top, an emitter voltage of 5.7, a base voltage of 5. So far, so good. But I expect the collector voltage to be lower than my base voltage, and it's not. If the collector voltage really were 8.6 volts, it would mean the current needs to flow in this direction through the transistor. And it can't flow in that direction through the transistor. Therefore, this voltage is probably wrong. This voltage is probably closer to about 5 volts, and this transistor is saturated. Once we find that the transistor is not in the forward active mode, we have to question all of the voltages and the currents that we've previously calculated. In this case, the real emitter voltage is closer to about 6.6 volts, and the real collector voltage is nearly 6.5 volts. These voltages can be obtained through simulation, but it's a terrible way to design a circuit unless you only want the transistor to switch on and off. We have one more example here to look at to finish out this video. When I look at this circuit, by inspection, I can tell that we're probably going to have some kind of an issue here. Now, we have the high voltages at the top and lower voltages at the bottom. The arrow's pointed in the correct direction, so it might be forward active. But the problem here is that the resistor values on the left are more than a factor of 10 higher than the resistor values on the right. That might cause the base current to be non-negligible. Let's see if that's the case. Well, let's start off by assuming that the base current is negligible, and if I neglect any base current, then I can assume that the voltage here at the base is nearly 5 volts due to the action of the voltage divider of these two equal resistors. The real base voltage, though, is probably a little bit higher than that, or perhaps a lot higher than that, depending on how big the base current is going to be. But assuming that it really is 5 volts, then I can add 0.7 to it in order to find the emitter voltage. In this case, it works out to 5.7 volts. The emitter current can then be found by applying Ohm's law, or V divided by R, to my emitter resistor. Here we get 43 milliamps. If we assume that the same 43 milliamps flows down here through the collector, then we can find our collector voltage. V equals IR, which here gives us 4.3 volts. So far, so good. We have 10 volts, 5.7 volts, 5 volts, 4.3 volts, and ground, nicely arranged from high to low. So the transistor is probably in the forward active mode, but was the base current negligible? We know that our base current can be approximated as our collector current divided by beta. Let's assume here that beta is about 100. So this is going to give me about 0.43 milliamps as my base current. How does the base current compare to the current flowing down through this resistor? Let's call this I. I is about 5 volts over 10 kiloohms, just Ohm's law across this resistor, or 0.5 milliamps. Unfortunately, the base current is not negligible when you compare it to the current I. These numbers are nearly the same. This means that something is wrong, and in this situation, it's very much my base voltage that's wrong. If we simulate this circuit in order to get reasonably approximate guesses for these voltages, we wind up with 5.8 volts at the base, 6.5 volts at the emitter, and 3.5 volts down here at the collector. If you were to make an amplifier like that, it would cause the gain to be reduced beyond what you would expect from the calculated values. In any case, it's not usually a good idea to design an amplifier where the base current is not negligible. In any case, it's still in the forward active mode. I hope you got a lot of practice here doing biasing with PNP transistors. In the next video, we're going to apply what we've learned to build some proper amplifiers using PNP transistors.